Welcome to week 8. And in week 8, we're going to talk more about network clustering. We've talked quite a bit about the clustering coefficient and what it means to have a cluster in a network. This week's set of 3 videos is coming from the material in chapter 6 of your book. So we've talked, as I said, about network clustering, and we know what the clustering coefficient is. And the clustering coefficient gives us a measure of how clustered the network is. But what does that mean exactly? It means that if you have a high clustering coefficient, that each vertex is likely to be in at least one cluster. And what is a cluster? In terms of a graph or a network, we've thought of a cluster as a dense subgraph. So what does that mean? It means there are a lot of edges induced by that set of vertices. But what do the edges mean? We say that 2 vertices are connected by an edge if they are similar in some way. So how we interpret a cluster and how we find clusters in a graph depends a lot on how the graph is constructed. If we think of a network, we want to look at the network and be able to look at it in a global way, the overall structure of the network, but we also want to look and see how each vertex in general, what properties vertices have with their neighbors. So the clustering is one way we can look at a network in both a local and global way almost simultaneously. We can view a vertex and how it interacts with its neighbors within the cluster, but in turn, we can look and see how do the clusters interact with each other, giving us a more global view. This is especially important when we're looking at biological networks. We want to understand the biological processes that the network is going to model for us. So we need to be able to look at individual members of the network as well as how they all interact. For example, in our protein interaction networks, we have each vertex represents a protein, and 2 proteins are connected by an edge if they interact. So proteins can come together and form what is called a protein complex. They can actually bind together. So this is how we're defining similarity in a protein interaction network. A gene interaction network, genes don't actually come and bind together. So when we say a gene-gene interaction network, what we're saying is that the genes are similar if they tend to be either upregulated or downregulated under the same circumstances, or at least similar circumstances. So we model a biological process with a network. It depends on how we're defining those edges as to how we interpret the clusters. And we also need to define how we want to determine the clusters, and that can vary as well. So it depends upon how we've constructed our network. In much of the literature, or even textbooks, when we look at cluster analysis, the analysis applies a type of, say, statistical approach. In this course, we're more interested in a graph theoretic approach. And it's difficult to find a textbook, as the author pointed out, that has a blend of graph theory and network science. And so that is one of the reasons that I selected this book, is because it does have graph theory and network science both used in the analysis of networks. We're going to be looking at some of the standard algorithms from theoretical computer science and applied graph theory in order to help us find clusters in a network. So the first algorithm that we're going to talk about is a type of what is called a greedy algorithm. So let's suppose with the illustration here we define this greedy algorithm. Suppose that we want to find a maximum weighted spanning tree. Now, first of all, recall a tree is a graph that's connected and it has no cycles. And if it's a spanning tree, that is a subgraph that is both a tree and has its vertex set the same as the entire graph. So we have a subgraph whose vertex set is the same, but the edges that we take are only those of a tree. And we want to find a spanning tree that's maximum weighted, where each of the edges have a weight assigned. So it's in a greedy algorithm, since we want a maximum weighted spanning tree, we take the maximum weighted edge at each step. We have a constraint. We don't want any cycles because a tree has no cycles. So we choose the maximum. We're being greedy under the constraint that the edges we choose cannot create a cycle. So we choose the edge 7, or the edge AB with weight 7. This gives us the edge AB, and we've chosen 7. And of course there is no cycle. We have a single edge. So we proceed. We want to be greedy at each point, so we look at all the edges. And the next edge we choose is EF, that has a weight of 6. Now that we have edge 7, or edge AB with weight 7, and edge EF with weight 6, we have two disjoint edges. The graph that they induce has no cycle, so we keep going. The next edge we choose is FD, because it's the next heaviest weight. And so we have 3 edges so far. Now, after choosing those 3 edges, we have a choice. The next largest or heaviest weight is 4. And we have 2 edges, EC and FC. We can choose either one. So let's suppose that we choose FC or CF. So now we have 4 edges with weight 7, 6, 5, and 4. The next heaviest weight is the other edge weighing 4. But now our constraint kicks in. If we choose the edge EC, we generate the cycle ECF, which is forbidden. So we can't choose the second edge of weight 4. We discard that edge and proceed. The next heaviest weight is 3. And we can again choose either CD or BD. So if we choose, let's see, let's choose BD. And then that picks up an edge of 3, of weight 3. Now there are 6 vertices. So any tree with 6 vertices is going to have 5 edges. So if we couldn't tell before, we know now that we have a spanning tree. We have a tree that uses all 6 vertices and the graph is connected. So the algorithm stops at this point and it returns the tree with the edges, the 5 edges that are weighted 7, 6, 5, 4, and 3 respectively, giving us a total weight of 25. So any other spanning tree, the sum of the weights of the edges would be no more than 25. Now in the literature, you're usually asked to find a minimum weighted spanning tree, which is fine. The same algorithm applies, except at each step you choose the lowest weight instead of the highest weight. This is just historically because the applications were often, the edge weights were considered a cost. And of course, if you're in business, you always try to minimize the cost. But in general, it could be minimum or maximum, as we've just illustrated. So let's do another example of a greedy algorithm. And this time, what we want to find is a maximum independent set. Recall that a set of vertices is independent if there's no induced edge. So we want to select as many vertices as we can. So it's a maximum size, but such that it does not induce, the set has no edge induced. So that's our constraint. So if we're wanting the fewest number, we want no edges in our independent set, We want to choose perhaps a vertex of minimum degree because that has the fewest number of edges incident to it. So we will start with, say, the vertex A. Now, since we want to build an independent set because of our constraint, we can exclude B, C, and E from our consideration if we've chosen A, because those would induce an edge since they're adjacent to A. So we proceed to select either D or F, because that's all that's left. We could choose, say, D, but then we would have to exclude F. All of the vertices have either been chosen or excluded, and so the algorithm terminates and it returns A and D as a maximal independent set. Now, A was arbitrary. We could have started with any one of the other vertices of degree 3. And so we could wind up with the algorithm returning, say, B and E, two very different vertices. Why is this not a problem? Because we're interested in the number of vertices that we can construct. It's the maximum number of vertices in an independent set. So even though the algorithm may return two different vertices, the number of vertices will always be the same, and in this case it will return 2. So the independence number is 2. Now, we're going to apply these algorithms in the next video to look at some clustering algorithms. And as we mentioned, most algorithms or many algorithms in the literature on clustering are based on statistical analysis, where we're going to use greedy algorithms and other types of graph theoretic algorithms. The two greedy algorithms that we saw in this video are the algorithm for finding either minimum or maximum weighted spanning tree and the maximum independent set. Now, one of the algorithms that we're going to look at next is the clique. Now, a clique, as you recall, is a complete subgraph. So why would finding a maximum independent set help us with finding the opposite? Because if no edges are induced in a clique or in an independent set, every edge is in a clique. Well, if you look at the complement of your graph, every independent set would induce a clique in the complement. So we'll talk more about that next time in our clique-based clustering algorithms.